Hello, thank you for joining us today as we delve into exciting breakthrough in battery technology, the novel lignin-coated anode designed to increase voltage in galvanic cells. Lignin, a complex and abundant polymer commonly found in plant materials, has the potential to increase voltage in batteries. One of the key applications lies in the realm of automotive vehicles. Imagine having a solution to lead-acid batteries when having challenges in hot and cold temperatures, translating to improved performance.
The independent variable is lignin, the varies temperatures and time. The dependent variable is the electrochemical voltage, and which would be manipulated by lignin. The control which stayed consistent throughout the experiment would be the batteries that do not contain lignin on their electrode and lignin batteries at room temperature. Picture a gray box meticulously filled with sulfuric acid containing two lead plates and two lead dioxide plates, creating an environment where this natural polymer interacts intimately with the electrode of lead. To record the voltage in amps, we used a voltmeter.
The control group batteries are defined by lead acid batteries with and without lignin at room temperature of 22.2 degrees Celsius. To set up the control group batteries, we measured 60 milliliters of sulfuric acid. This was then poured into respective battery. The average range voltages at each time are depicted in the slide, comparing the control of with and without a lignin-coated anode.
A similar setup was used for the batteries above the temperature of 22.2 degrees Celsius. We used a hot plate to achieve the warmer temperatures of the battery. The slide shows the ranges of the voltages at each time, showing the temperatures of 33.3 degrees Celsius, 42.2 degrees Celsius, and 51.1 degrees Celsius, comparing the difference of with and without a lignin-coated anode.
The same setup was used for batteries below the temperature of 22.2 degrees Celsius. We use a cooler to achieve the colder temperatures of the battery. The slide shows the ranges of the voltages at each time, showing the temperatures of negative 22.2 degrees Celsius, 15.6 degrees Celsius, and 6.7 degrees Celsius, comparing the differences of with and without a lignin-coated anode.
For analysis of the differences between a lignin-coated anode and a non-lignin-coated anode for lead-acid-based batteries, our primary findings were based on the average rate of change in voltage over time, which we calculated from the average voltages over 2 minutes at each of the 7 temperatures. Here, highlighting the figure 1. The average rate of change of the novel lignin-coated anode is not only significantly greater than the lead acid, seen with a percent difference of 327.17% difference from that lead acid, but it is a positive slope while the lead acid is a negative slope.
Upon analysis for the effects that a lignin-coated anode has on the average rate of change of voltage over time for the temperatures highlighted here, there is no set correlation that could have been found between the temperatures above 22.2 degrees Celsius and that of the rate of change of a voltage. The percent differences between the novel lignin-coated anode and the lead-acid battery were ranging from negative 27.78% difference to a 94.44% difference.
The betterment of our analysis comes from the average rate of change of the voltage for batteries that were below 22.2 degrees Celsius. In all these temperatures, there was an increase in the voltage over time, suggesting a positive correlation between the change in voltage and having a lignin-coated anode. The largest increase was at 15.6 degrees Celsius, where the slope not only changed from negative to positive, suggesting an increase in voltage with a lignin-coated anode.
The novel lignin-coated anode not only produces a faster rate of change in voltage over 2 minutes, but also delivers a higher amperage than that of a traditional lead-acid-based battery. In figure 3, we can see that the finding is most especially true in the temperatures below 22.2 degrees Celsius, with the percent difference between lignin and a lead acid ranging from 50 to 87.7%. Such a significant increase in amperage rate of change in the voltage suggests that in colder temperatures, the addition of a lignin-coated anode improves the current.
Here, figures 4 and 5 again demonstrate the differences between the slopes of traditional lead acid batteries and that of lignin-coated lead acid batteries at different temperatures.
In conclusion, the addition of a lignin-coated anode to a lead-acid battery has major and positive implications regarding in terms of average rate of change of the voltage and the amperage over time in comparison to traditional lead-acid-based batteries, most especially in temperatures below 22.2 degrees Celsius. Lignin's atomic structure, composed of multiple benzene rings with delocalized electrons, allow for the high reactivity with various chemicals and potential applications to material science.
The project's outcomes paved the way for several practical applications and advantages. Since lignin is the second most abundant biological material, the lignin-coated anode presents an eco-friendly alternative to increased voltage and amperage in a lead-acid battery. The validation of all three hypotheses is significant as lead-acid batteries are widely used in automotive and stationary energy storage, proving to be a major breakthrough regarding the concern of lead-acid batteries in cold temperatures. Thank you.